Good afternoon, everyone. I am Barry Shoke with KCI Technologies. Welcome to this session on automated data collection to identify infrastructure assets and assess the condition of those assets. I know you've heard a lot of great talks throughout the conference so far. This one is a little bit different. We've talked about this over the last couple of years with the conference that we wanted to bring in a different type of asset, meaning we're in transportation. We talk a lot about highways, bridges, and related assets along an infrastructure project associated with surface transportation on the highway side. This talk and the series of speakers you're going to hear from are going to focus more on the rail side. I'm sure you're going to hear some similarities in terms of approach or some things, hopefully, that will stimulate some thoughts on your end about how you could apply what's being done in the worlds of rail to what you do in your own area of infrastructure in terms of asset management, especially as it relates to automated data collection, as that helps you to assess the condition of assets using some analytics and other means. So we have a broad array of speakers. I'm not going to take a lot of time on my introductory comments. I'm going to encourage you, please, as you listen to the comments today, listen to the sessions, to use your chat session or your Q&A and to type questions or comments you might have that our speakers can address at the end of the sessions. We're going to go through the speakers, and then at the end, we will take some time for Q&A and discussion related to your comments you provided. So thank you for attending this session. I am now going to introduce you to Todd Houston. Todd is a member of our firm, KCI Technologies. He's a senior project manager that does data analytics, and he's a rail specialist. So he's going to introduce his team and take over the presentation. Todd, welcome, and thank you. The floor is yours.
Thank you, Barry, and welcome to everybody attending. I've been working with railroad track data for over 20 years. And today I'm going to do a high-level overview of the types of automated inspections utilized in the rail industry to measure and assess the condition of the track and the right-of-way. And the presentations following me in this session will discuss in more detail how the data is integrated into asset management programs. Some automated inspection technologies have been used in railroading for nearly a century. And today, railroading is in the big data era with huge volumes of data generated at a relatively high frequency. And the information derived from that data feeds the safety, maintenance, capital programs, and overall asset management programs of the track owners and maintainers. Railroads have been a successful transportation mode for over 200 years, and improvements in engineering and technology have allowed them to continue flourishing. Because the track is such a critical part of keeping the railroads in business, it's important to understand the track structure and why it's essential to maintain and the consequences of failure. 5 major engineering functions of the track are as a guideway to keep the train on the track, efficiency, the low rolling resistance maintains a smooth ride, structurally to dissipate heavy loads into the ground, resiliency, the elastic response of the track attenuates degradation and maintains durability. And then drainage, because everybody knows water causes problems. These images show examples of what can go wrong if track conditions become compromised or if train operations don't match the capability of the track. And therefore, it's critically important to inspect and maintain the track to prevent accidents. For some perspective, since this is an asset management conference, the magnitude of assets a railroad has to manage, we consider either the 2 Class 1 freight railroads that operate in the Western U.S. As examples, the BNSF or the Union Pacific. Each of those railroads has roughly 32,000 miles of track, which is 64,000 miles of rail and in the neighborhood of 100 million cross ties. And that's just 2 types of assets, but they also have other track components, structures, communication and signaling systems, facilities, and other infrastructure needed to operate the railroad. So that's a really large number of both linear and discrete assets to manage distributed over a large geographical area. The high energy nature of moving trains means accidents can be deadly, damaging, and expensive, from direct cost of cleanup and restoration to claims and costs of delays to their operations. And of course, when these happen, they're usually visible to the public. The industry, from both the side of oversight agencies and the side of the railroad owners and operators, has built a framework for managing track safety and quality that includes various sets of standards, inspection programs, performance metrics, and significant investments in maintenance and capital programs. Keeping trains on the track and moving at maximum safe speeds is good for business, and it's good for the industry's reputation. It's always been necessary to inspect the track and to find and fix the problems. In earlier days of railroading, this was done by human eyes and manual measurements. Technology has changed the nature of inspection to allow more automation and more data to help those responsible for maintaining the track to become faster, more accurate and objective, and have the capability to spot developing problems earlier. While human inspectors are still utilized over the past century, a number of technologies have been developed to augment human inspectors and to maximize their productivity. These have been mounted on various types of vehicles, such as high rail, dedicated inspection cars, revenue service cars and locomotives, and more recently on aerial drones. There are also sensors installed along the track that can provide a steady stream of remote data. So there are quite a few systems and types of data currently utilized to feed the railroad's inspection program, monitor the conditions, and help decision makers understand where and when maintenance interventions or rehabilitation may be needed. So now I'm going to go through some of the automated systems currently in use. And while this isn't an exhaustive list, it covers a large chunk of the automated inspection data railroads are using to manage their track assets. First up is track geometry, which is the three-dimensional shape of the track as it relates to the positions of the rails. Automated track geometry measurement has been in use for almost a century, believe it or not. Modern systems use lasers to determine the position of the rails and an inertial measurement unit for changes in vehicle position as it measures the track. This system is used to check if the track is at risk of causing the wheels to come off the rails, and also if the track may cause high vehicle dynamic response that creates a poor ride quality. Process track geometry data provides several standard measurements such as track gauge, horizontal and vertical alignments, cross level, and several derivatives of those measurements. And the railroads use that information to stay in compliance with track standards, impose slow orders on trains when they don't, and determine trends over time that may give an early warning of a developing geometry problem. Rail flaw inspection is used to find cracks in rail that can form from metallurgical imperfections during the manufacturing process and by fatigue or impact from trains and maintenance equipment. There are several technologies used to find defects in the rail, with the most common being ultrasonics. Ultrasonic testing has been in use for nearly 100 years, and these systems look for deviations from a normal response that may indicate some kind of irregularity within the rail. These irregularities could be cracks that, if allowed to continue growing, could lead to a broken rail and potential derailment. Railroads use that data to remove the defects and to keep track of the rail's performance over time to determine when the rail may be fatiguing to the point it's more optimal to replace the rail rather than keep maintaining it. The rail surface inspection, the surface of the rail is inspected for surface cracks and other flaws caused by wheel contact, and also for corrugation that causes both noise and vehicle dynamic response. Some of the technologies used for surface condition include machine vision imaging and magnetic flux measurement to find irregularities that could cause material separation at the surface or propagate into the rail to cause a full rail break. For corrugation, systems use laser profiling, accelerometers, or even noise measurement to determine if there are periodic surface variations. And this is often caused by train acceleration and braking, or harmonic dynamics induced in cars by rail support conditions or car suspensions. And the data from these types of inspections are used to plan for rail grinding, which is a process of removing the top layer of metal from the rail to remove the surface cracks and also to leave a smoother and more ideal surface profile for wheel-rail contact. Another mitigation for surface problems is to introduce friction modifying substances to the wheel-rail interface to control the friction level without losing too much wheel traction. Next is the measurement of rail profile. The rail's cross-sectional profile is measured using a laser system. The cross-section can be used to determine the original size of the rail and compare that to the railroad's asset database, which historically has not always been complete nor correct. The cross-section is also compared to the original new rail profile to calculate wear. Wear data is used to ensure the rail is within wear limits and to forecast when it might reach its limit. High wear rates may also indicate other problems such as high vehicle dynamics, worn wheels causing undesired wheel contact, or the track design not being well matched to the train operations. High wear rates also might lead to mitigation efforts such as using friction modifying substances to reduce wear rates. Another use of the rail profile is for rail grinding planning. As mentioned on the last slide, grinding is used to reshape the rail for more optimal wheel contact, and the measured rail profile is used to plan the right amount of metal removal in the right location. Next is inspection of ties and plates and fasteners. The condition of cross ties and fasteners is important to the resiliency, stability, and durability of the track. Ties will crack and warp and mechanically wear from movement at the rail tie interface. Fasteners can break, deform, or become loose and lose their ability to hold the rail in a fixed position on the tie. And there are several systems used to assess the condition of the ties and fasteners. Commonly, they capture a 2D image or a 3D digitized height map of the track and use machine vision algorithms to parse the data into components and perform classification, measure dimensions, and assess the conditions of the components. And there's even a system being used in the industry to X-ray the interior of wood ties to find rot or deep cracks that are hard to find by other methods. And the resulting information is used to stay in compliance with track standards, plan spot maintenance for localized problem areas, and plan large-scale capital replacement projects as the ties along segments of track degrade over time. There's another assessment called for track strength, and while the large proportion of train loads is in the vertical direction, wheels do impart lateral loads on the rails, and it's important for the rail and the track structure to resist too much movement under those loads to prevent the wheels from falling into the gauge or prevent the rail from rolling over. And one technology that's been developed for this test is called Gauge Restraint Measurement System, or GRMS. The GRMS apparatus applies loads in both the vertical and lateral directions and measures the variation in the track gauge when it's loaded. And the information from this inspection system can point to problems with fasteners and defective ties unable to hold the rail in place, and it's used for maintenance planning for ties and fasteners and even ballast. The ballast layer provides structural support to the track in both vertical and lateral directions, and insufficient ballast can lead to bad track geometry, excessive movement of the track, and higher pressures on the subgrade. LiDAR is the most common technology used to measure the rail surface, or the surface profile of the ballast layer. The 3D point cloud that comes from LiDAR is compared to the design profile to calculate the magnitude of deficiency or excess, and this information helps the railroads quantify and plan for restoration of the ballast layer. To inspect the ballast and subsurface, sorry for the pause, I had a screen go out. To perform at its best, the ballast layer should be clean and facilitate drainage of water away from the track. If debris and fine particles infiltrate the ballast layer, known as fouling the ballast, it can lead to trapped water and more rapid degradation of the ballast rocks. To assess the condition of the ballast, ground penetrating radar is the most common technology used. GPR is used to determine the thickness of ballast, and subballast layers calculate a ballast fouling index and determine high moisture areas where water may not be draining effectively. The information from GPR inspection is used to plan maintenance such as ballast cleaning and undercutting, and may indicate larger issues with drainage away from the track that should be mitigated. If we think of the track structure as a beam on an elastic foundation, the vertical stiffness of the track will influence how much the rail deflects under load. In addition to preventing excessive deflections that will degrade track components faster, variations in track stiffness also will cause dynamic responses in the rail cars that can make for a bouncy ride. The system was developed to measure track deflection and help identify soft spots in track that may indicate problems with ties, rail joints, ballast, subgrade, or even sudden hard spots in track commonly found at boundaries of track features such as bridges. And this information is used to guide maintenance and mitigation efforts aimed at providing a more uniform stiffness along the track, and also where structural methods for smoothing transitions between softer and stiffer areas of support may be implemented. There are lots of objects around a railroad track, from bridges and tunnels and station platforms to vegetation, and for some railroads, the overhead catenary system that supplies power to the trains. LiDAR is commonly used to create a 3D point cloud in the clearance envelope, simulating a train can be run through the point cloud to find any potential collision hazards. Lasers often are used to measure the position of the overhead catenary wires to ensure trains will maintain consistent contact. And also, if a railroad's planning to reposition their track laterally or vertically, they can use the point cloud for planning to ensure they aren't introducing new collision risks. Most people will associate temperature measurements in railroading with the buildup of compressive axial stresses on hot days and the risk of track buckling. But performing a thermal scan of the track using infrared sensors can help locate cold and hot spots along the track. Cold spots may indicate standing water and poor drainage and lead to ballast maintenance or other drainage mitigation efforts. And hotspots may indicate stray current in electrical systems and lead to power system investigations and maintenance. So far, all the inspections I discussed have been measuring the track and its components directly, but a different way to assess the overall health of the track is how a train responds while running over the track. And to do that, vehicle track interaction systems, or VTI, are mounted on railbound cars, and they measure the forces on the wheels and accelerations of the trucks and the car bodies to assess how trains respond to the track during actual operating conditions. And this system may find track problems that are not so obvious from the data from other inspection systems, and so it kind of acts as a supplementary type of inspection for maintaining good train dynamics and ride quality. So that's the end of my introduction of all the technologies, and that's a lot of data types that railroads are collecting. That data needs to be used effectively to understand the condition and performance of the track and to get the most information and value from the data. A robust asset management program will include effective data management, analytical and modeling tools to interpret and predict, work order management, and tools to aid in the prioritization and planning of maintenance and capital programs. The information extracted from the data informs the various decisions railroads make to keep their tracks safe and performing up to the needed level of service, and how to most optimally spend their maintenance and capital budgets. There are usually multiple alternatives for how a railroad can respond to a situation where track is degrading, and they need to consider factors such as safety, risk, route criticality, budget, their labor force, and the degree of difficulty needed to perform any work. One option is always to do nothing and accept the risks to safety and operations. Another is reactive spot maintenance, where only track out of standard gets repaired. But we're moving into the era where proactive maintenance aims to continuously monitor conditions and perform large-scale planned maintenance. So there are fewer instances of track getting out of standard. And of course, there will come a time when the best solution from both engineering and economic perspectives is to hit the reset button by replacing the track or certain components out of phase. So in summary, The data collected by the railroad is vital to understanding the past and assessing the present and predicting the future. And by putting it all together, they can produce a big picture view of the health of their infrastructure and direct the resources to the most critical needs, keep the trains on their tracks, and keep the trains on time. So the presentations after this will dive deeper into practical applications of inspection data and how it's used in asset management programs. Thank you all for joining me today. And at this time, I'm going to introduce Brad Spencer from CSX Transportation. He's going to be talking about their rail inspection and management program. Brad is Director of Track Testing at CSX, and I'll note he's also a Penn State graduate. Brad, over to you.
Okay, well, thank you. Let me pull up my show here and start off. Like Todd had mentioned, my name is Brad Spencer. I come from CSX Transportation. I'm in Jacksonville, Florida, and I manage the track testing program here at CSX. And as you can see by what Todd went through, there's quite a lot of data sources, and as you all know, and the big topic nowadays is how to handle big data, and it really gets challenging with these. A lot of the test systems are mobile and in the field, but we'll discuss that a little bit more as the presentation begins. So I'm going to talk about rail testing specifically, and a little bit of the future, but I'll start off with what we're using today. And usually it's referred to non-destructive testing, or NDT, and I'm going to refer to it as NDT. Just means you don't have to cut the rail or anything else to do the testing. It's not a non-contact system for the most part in most cases, but it doesn't do any damage to the track itself. So it uses equipment that will efficiently and reliably assess the dimensional, internal, and external integrity of the rail in order to meet or exceed standards and specifications. And NDT provides thorough characterization of the rail and outputs real-time data regarding rail quality, using methods to internally test for inherent defects from manufacturing and fatigue defects from heavy use. CSX is a Class 1 railroad with very heavy tonnage on many of our core routes, and that's typically, now that the manufacturing processes have gotten so much cleaner over the years, we have a lot less problem with the manufacturing side. Most of our defects and issues are from fatigue from use, which is good. That's how we make money. But we need to manage that. Rail inspection data is used to provide the integrity of the rail, operator feedback, and facilitate continuous process improvements. So this presentation, I'm going to talk a little bit about something that usually nobody likes to talk about, is regulation guidelines and industry guidelines. But it's kind of interesting because we've had some newer things happen recently, and I'll get into that in a little bit. And then the equipment, and you saw some of that equipment in Todd's presentation, and some of the technology on the horizon. Some of it's being used, some of it's almost there, or we're working towards it as an industry, and what the observations are from our testing program here at CSX. So you saw something similar to this in Todd's presentation, but to look at this carriage is the rail testing, the typical rail testing platform on CSX. So you have the brushes on the right with the there's a transducer between the two, a pickup transducer. What that is the induction side of this carriage, and on the other side there's two wheels there that have fixed angle ultrasonic transducers inside liquid inside those what they call roller search units. which that's what they look like. But that's our ultrasonic side of that carriage. And then what you don't see here is we have a visual system on all our trucks that actually, when some pretty simple AI determines what we call blocked out in our testing, which is something that we need to look at or pay attention to in the screen, it'll actually take a picture of that location so the operator can relate it to what the transducers on the carriage are actually seeing. So that's our basic system. But so here's kind of what we're guided by, because we have federal regulations, and it's the Code of Regulations, Title 49, Track Standards, Part 213. That sounds exciting, doesn't it? And this is typically the book that it's in. The picture is, and this particular book is just regulating it's pertaining to classes 1 through 5. We call the speed of the track is based on class. So, for instance, freight speeds from 0 to 10 would be class 1, and 10 to 25 is, or 11 to 25 is class 2, and so on, up to freight speeds of 70 miles an hour, which is class 5. CSX does have some class 5, but most of our core routes are class 4, which is 60 mile an hour freight speeds, 79 passenger. So this regulations are enforced by the FRA, the Federal Railroad Administration. The FRA track safety standards. General focus is the track structure, track geometry, roadbed, rail inspection, which is what we're going to focus on here, and the frequency and the quality of the railroad's inspection, the remediation requirements of the detected defects that we do find, and how we keep track of everything is kind of some guidance for all that in these standards and regulations. So one thing that's kind of new and exciting, and I know it's hard to be too excited about regulatory and industry guidelines. Most people get a little winded, but one thing I can say is we used to be guided by minimum rail inspection intervals based solely on tonnage, and that sounds good. You run so many trains over the track, and you have to inspect it depending on how many trains you run over the track, and that seems like it makes sense, but it really doesn't. It's more the accumulated tonnage on the track. What would be nice is if you could base your testing frequencies based on fatigue. So that's what this is kind of about. So the railroads can determine their minimum inspection intervals based on the following. So we do rail service failures, which rail service failures in the railroad business means it's a broken rail. It interrupts service, and that's by year and by mile. So we're allowed to have, if you look at point 1, we can have one service failure on a 10 mile an hour or 10 mile section of track in class 4 and 5, and the FRA has a limit of 0.1. So if we fail to stay within that rail service failures, then we have to test more frequently. And then the other side of it is if we have passenger service, or if we have hazmat on the line, then we also have to test in class 3 as well. So that's up to 40 mile an hour freight. It would be class 3 for hazmat and class 3 for passenger. And if we have both, of course, you can see the trend. It's going to be a difference of 0.02 instead of just 0.01. And that means you can only have 8 service failures per every 100 miles instead of 10. So it gets more restrictive with the more sensitive the freight is in passengers. So the only types of service failures the FRA uses for this determination is vertical split heads, which is a longitudinal defect, and I'll show you that here in a second. Transverse defects and transverse fissures and compound fissures. That probably doesn't mean a lot to you, but I'm going to show you the what a transverse defect is anyway. So, in-track rail testing, like I said, it's a mobile platform. You can see the top picture there is a rail-bound platform. It can't leave the rails. It's got metal wheels. The bottom one is a truck that you can take on and off. It's a high rail truck. And you're looking for defects internal to the rail typically, and that's things you can't see with the human eye. And the primary methods for doing that, like I said, was ultrasonic, which has fixed angles of ultrasound being shot into the rail, and then it's coupled with typically water, but you can use other things as well. And so it goes from the wheel through the water to the rail, and if it hits a reflector, it bounces back, and the system can put all these angles together and tell you a lot more information about what the reflector is. And then there's magnetic induction, which is those contact brushes that you saw on the right side of the carriage that we saw earlier, and that kind of complements the ultrasonic. The ultrasonic is your main testing method, and the UT. Not all companies use the induction, but it complements that ultrasonic. Like I said, it actually runs a current from one brush to the other brush, and induces a magnetic field in the rail. And then there's coil pickups in that sliding bar that I showed you earlier, and it can measure changes in the magnetic field, and that's less affected by rail wear. So if you get into heavy curves that have a good amount of rail wear, that the magnetic induction is less affected by how worn the rail is in the curve, unlike ultrasonic, which is sometimes difficult, and you got to readjust the alignment of those RSUs. So the average speed of one of these trucks when we're using a truck is 5 miles an hour, a little bit hair more on our railroad. And it doesn't sound very exciting because it typically isn't. You can test up to 15 if you're on really good rail and there's not a lot of reflectors in it, since you know what we're looking for. It makes frequent stops. So it stops, it backs up, it can rerun, it can realign carriages, rerun it again. When they suspect a defect, the operator gets on the ground and actually uses a hand ultrasonic A-scan type equipment, which just, depending on what transducer he puts in there, depends on what angle he's using. And he searches for a defect, and he can measure the size using the hand unit, and then he marks the rail with the defect, with the appropriate defect. And then, of course, it's also recorded in the computer and sent to all our systems, and it's tracked automatically, make sure it's repaired correctly. There's a lot that goes. We're not going to get into all those details of how everything gets into our system, but there's quite a lot to track. And depending on what size of the defect and what kind of defect, there's all kinds of schedules that have to be done per regulation. And so if it's a real big defect and the risk is a lot higher, the remediation has to be done a lot sooner than if you have a very small defect, things like that. I could do several hours of training just on that topic alone. So that was our typical way until just recently. We've been working for the last decade, really, to have something like continuous rail testing, which is what that is in this case, we're using the rail-bound equipment, and we just run it across something, and we don't stop, we don't back up, we don't hand test it. We just collect data, and then after the data is collected, it gets sent to a central location where we have a processing center, and people review the data and they compare it to the data that we collected the last time and what we've already looked at and what we already checked. And then they'll send a high rail vehicle like the one on the lower part of that screen to go out and look at all the suspect spots. They're not defects until somebody actually gets on the ground and looks at them, because there's a lot of cases where ultrasonics give you like a false echo, and it really needs to be hand tested before you can consider it a defect. Although there are certain indications that could lead to that it may look like a very large defect, and in those cases we kind of prioritize those. So when the guy goes out to follow up with this high rail truck, if he has some of these large defects or large suspect defects, then we go to those first, even though it's not always the most convenient thing to do, but we prioritize it based on what could be. And that whole idea, again, is to lower the risk. And everything we do in testing is really to mitigate risk, and that's one thing you got to realize. So some things you cannot eliminate 100% all risk, but when you're moving freight, heavy freight on steel rails, but you do everything in your power to get as low as possible. So, and that's what our testing programs are all about. So this whole process doesn't sound like a huge change, but it really was. And it's a lot more efficient way to use track time. We don't sit out there for hours and hours and hours, especially when we're running so frequently as we do these, because we tend to cover a lot more track with this method than we do with other methods. So we get there earlier and we test more frequently. The more frequently you test, the better, because the comparisons from the last run are a lot more accurate, and there's a lot less variables. And pretty soon, if you're running along, and frequently enough, that your suspect counts go down and down and down, and the guy that's got to go out there and with this pickup truck has less and less, and he can go to it quicker. And it's just a really good way to get out there and test, and it also, like I said, gives you that capability of looking back at the last run and doing that comparison. That is really a powerful tool, and we don't have those capabilities in a normal stop and verify truck. So the other method is stop and verify, S&V, and this one is CRT. Unfortunately, these regulations took 10 years because it's very difficult to invest in technology when the government and regulations constantly restrict the advancement of technology. So I'm not going to be here to preach the bad side of regulation, but it really does have a horrible side effect of not advancing technology. And in this case, no rail test company really wanted to invest in this technology, especially on these rail-bound vehicles. They're very expensive to buy. This particular vehicle is a 1940 something, so that this one wasn't very expensive in today's dollars, because if you could look at depreciation, it's been in a negative column for a long time. But we wanted to buy a new vehicle, new technology that's really designed about this technology. There could be a lot more improvements on this vehicle. It took 10 years to actually convince the FRA, really, because the union has some say in it. So it's kind of there's a whole bunch of things that go into changing regulation, and it's a difficult thing. So let's talk about the rail defects themselves. I told you that we'd talk a little bit about this. So you can see this is a vertical plane. You're looking at a piece of rail, and this is a couple foot long section. It's, and you can see the horizontal plane, and then you see the transverse plane. So when we mentioned earlier about a vertical split head, that means there's a split head that's in that vertical plane. That there's usually a seam or a shear that wants to separate off, and it's a very dangerous defect. And you look at a transverse defect, you gotta it'd be in this plane here, And you can see where that would be a very bad defect. Not that the horizontal plane is has no risk, but it's a lot less risk than those two. So, and then of course, in the web of the rail, we could have rail defects. So we could have defects in the base, where we weld the rail together, or where there's damage from a derailment or something like that, or there's all kinds of ways to create defects as well. But most of our biggest problems are, when it comes to fatigue, are vertical split heads and transverse defects. And that's why the FRA only uses those 4 types. Mechanical defects is what we would call, damage or welds. And base defects are something that we can't, with the current technology, we can't really test the defects in the base. So that is something maybe you can put on your whiteboard and figure it out for us, because we've been trying for a long time to figure out a good way to economically test the base of the rail in service. They can do that when they're manufacturing it, of course, but they can't do it when it's in service. We can on a small scale, but we can't when you're trying to cover 20,000 miles of track. So not efficiently and not with a normal price tag. So this is those transverse defects. This particular one is a TDD, just a transverse defect. It's not a transverse fissure. The difference between that is a TDD is created by fatigue, and the transverse fissure is something that was inherent to the rail. It was manufactured into the rail. Like I said, we have a lot less problems with those recently in the last 30 or 40 years. We're finally getting most of our older rail out that had a lot of manufacturing issues. So these are the bigger problem for us between the two of them, between compound fissures and transverse fissures and transverse defects. So some of the challenges, I'd already talked about the wear. You heard Todd talk about rail surface. Rail surface is a real issue for this testing, because you got to be able to get through the surface with your ultrasound to be able to test the interior of the rail. So if we have a lot of rail surface, that affects the ultrasound and the reflections back. So that's a problem. The geometry, the oxidation, like if we have really heavy oxidation on the rail because there's a lack of traffic, or just not being used, and then say it hasn't been used for a long time, and then all of a sudden they're going to start running trains across it, and you got to get out there and test it. A lot of times you can't get through the oxidation to test it. You got to run some light locomotives across it a couple of times ahead of you or something like that to make it possible. Grind marks. So when they grind a rail, to get the geometry back of the rail. And those marks can affect it because the marks start reflecting all over the place, the ultrasound. So if you have surface debris, leaves, grease, oil, snow, ice, anything that's on the rail, typically it's not a big problem, except in the fall or in the winter with the ice and snow and the leaves. We do lubricate the track, so we don't wear the curves in the surface of the metal as quickly. So we have what we call greasers, and the greasers, every time the train rolls over, it picks up a tiny little bit of grease and usually puts it on the gauge face of the rail to minimize the wear and minimize the rail surface conditions. And then, like I said before, there's alignment of those roller search units. And then the magnetic induction, it has problems with liftoff, the probe liftoff, because if you're going on, especially over special track works or joints, the wear on the slides and the brushes, it's a constant maintenance game on that thing. It picks up a coarse grease and debris. It's a mess. And low sensitivity. Test hardware damage at the offsets in the track and special works, like I said. So that's pretty much how we measure it. We got those two main methods. Now there's a lot of technology that we're starting to use or is in the process of being developed. And this allows the rail testing to be more on an autonomous platform, although that would be the goal. We're not there yet. It would be nice to be able to put this system on a box car and just put it out there in our fleet and have a bunch of them and run all over the place without any people on them. And, you know, all this data comes flowing in and we manage it all in our databases, and the end result would be a lot less expense, interference with the railroad operation, lowering the risk. I mean, there's so much advantage that you don't have people out there on the track, so you got a big safety advantage. There's just a ton of that would be the ultimate thing, is to move it into an autonomous platform. And of course, you don't want any contact with the rail. We can't be running around having to contact the rail on these autonomous systems. There's systems out there that monitor vibration, magnetism, a little bit different than how we were talking earlier with the induction, but acoustics, X-ray, gamma ray, thermal, all that stuff is a good thing, and it's all being developed towards more accurate testing. And we want to be able to do it at all speeds. We can't run at 5 miles an hour forever. Although one thing I didn't talk about was on that continuous rail testing, the CRT, or some people call it nonstop, is that's a lot quicker because you can, you know, collect the data, and it's a lot faster as you're collecting it. We can collect data up to 35 miles an hour. And then, of course, when you send a person out, they don't always have to be on track to follow up with that thing. So they could, if they only have a couple suspects to look at and they can drive into it, they can do that without even getting track time. So that's a big advantage too.
Hey, Brad, sorry to interrupt. We're running out of time here because we're on a time schedule to fit everybody in.
Okay, yeah. You want me to just go a little quicker? I'm getting towards the end anyway.
Yeah, I just need to wrap it up. Thank you.
Okay. Ultrasonic technologies, the phased array, guided wave, EMAT, laser, and air coupled approaches. These are all on the horizon. There are some companies that use phased array or are trying to develop it. And then, of course, machine vision, like Todd said. Drones, I was out working with a company with drones this morning. It was for geometry, but not for rail testing. And then, of course, the modeling and simulation, which is where you guys come into. So I'm going to shorten this slide and say, you know, of course, there's a lot of having all this data. It improves maintenance efficiencies, and hopefully we can reduce manual inspections, which and increase automated inspections. That will save money and time and people risk. And they're going to automate the whole inspection process and refocus those inspections on the places that have higher risk. So that's a big plus. And then the long term is use improving technologies to enhance the current capital planning process decisions. So the capital planning is the money we're going to spend in putting new rail in, ties, and things like that. So you know, you're reinforcing that with data, actual data, instead of some guy telling you that it needs it. So and then going to a full automation in predictive analysis is a little further out, 3 to 5 years kind of planning. And again, it's being proactive instead of reactive. And so this is the data management's probably one of the biggest technology drivers there is. People don't necessarily see it that way. So the new processes, the new management tools that we have allow us to assign, you know, have this feedback loop where we assign the risk, we test based the frequencies on it, and we do the testing and scheduling, and then it goes back into the inputs again. So this whole model and being able to control this model is absolutely critical. And that's what's really driving a lot of our decisions. That's a lot. It has improved so much over the last 10 years. And really, it comes down to all the decisions that we're making to get to that root of the risk. And it provides time to interrupt failure mechanisms, prevent incidents. So this is really the kicker. So here's our rail defect caused FRA derailments. And you can see these are only on the main line, and what we call FRA derailments have a set threshold. And this year it's $10,700. So anything more than $10,700. So this is the number of derailments that we've had since 2011. And you can see in 2019, we did not have a broken rail caused derailment on the entire CSX main line and siding network. We were the first class one in the industry to ever have zero for a whole year. So we are getting results. We're putting our capital in the right locations. And, you know, and it all comes down to this: is predicting the life cycles of the rail, enhancing rail flaw libraries, neurologic networks, increase accuracy and flaw detection. And then, of course, it's a vital national transportation system that keeps getting more efficient and make more money. And, you know, we don't require taxes, or we pay taxes. We don't use taxes. So we are on the right path, putting the money in the right places and reinvesting it in our company. And a lot of it is based on, you know, data management. Thank you. Sorry to run over.
Thank you, Brad. Great explanation of how automated inspection is keeping the rails from breaking. Next up are two gentlemen from the Washington, D.C. Metro, WMATA, to talk about their automated track inspection and maintenance management program. Ravi Amin is Director of Track Engineering, and Spencer Tchaikovsky is Manager of Division Engineering. Ravi and Spencer, take it away. Just remember, we're getting a little bit behind here, so just mind the time. Thank you.
Certainly. Thank you, Todd. And thank you, everyone, transportation, TAIM's attendees for this confrontation, this opportunity. This is WMATA's automated track analysis technology and data handling for maintenance decisions. We're going to speed this up a bit because we know we're short on time. I am Ravi Amin, Director of Track Engineering at WMATA, and my colleague co-presenting is Spencer Tchaikovsky, Manager of Division Engineer at WMATA and also Penn State grad. WMATA uses automatic track analysis technology to help assess track condition, leading to capital renewals and fiscal planning. WMATA's system is a 6-line mainline system, radially designed. We carry about 40 MGT on our heaviest line, which is an east-west running line. We have about 237 mainline track miles and 91 stations. Within the next year, will be. Sorry. Yes.
Your presentation is not showing.
I am sorry.
I don't know if Brad has to unshare his first.
Can you see my screen?
Not yet. Make sure you select the screen and then hit share.
Yes, that's what I forgot. Thank you. I apologize about that. Okay, should see my presentation now. Okay.
Yes.
All right. Thank you.
Sorry about that.
Not a problem. My apologies. So WMATA's 237 track mile mainline track system, 91 stations. We'll be adding 5 additional stations and about 22 additional track miles within the next year with our Silver Line Phase 2 part of the system being introduced. We, on average, carry 640,000 people per average weekday. That was pre-COVID-19. Today, we're about 13% of that number, unfortunately. WMATA has a goal to integrate automatic track inspections as part of our routine daily track inspections and to better inform on state of good repair. WMATA used automatic track inspections prior to 2011, but in 2011, we commissioned our own vehicle dubbed the TGV. This vehicle measures track asset condition and reports track conditions that do not meet WMATA's maintenance and safety standards. Various tests are scheduled throughout the year, including repeat tests, to allow us to do trending analysis within the same year, as well as comparing to past years, so we can understand the degradation of track. Data is automatically assessed according to WMATA standards and is prioritized for maintenance attention and action by engineering staff And this data is loaded into our linear asset management system, in which it's handled and manipulated for data analytics. The TGV has 4 core testing abilities, which is track geometry measurement system, ultrasonic testing, which we heard about from Brad, which is the internal rail health and irregularities within the rail, thermal imagery, track circuit frequency strength. In 2015, WMATA introduced the 7000 series vehicle fleet, our newest vehicle fleet. Approximately 750 of these vehicles have been delivered to date. These vehicles have the VTI measurement system loaded onto them to identify ride quality issues stemming from both track conditions as well as vehicle conditions. About 7.5% of these vehicles have the VTI equipped on them, and these vehicles operate daily, reporting track conditions in real time. The trains use the commercial cellular wireless network to report track defects in real time as they come about. And the VTI system measures abrupt lateral or vertical movement affecting the axle, the truck, or the car body of the vehicle. Data is reviewed and also can be loaded into our linear asset management system for further analysis. WMATA doesn't have all automatic track inspection capabilities in-house. We also contract out some services, particularly which is tie condition and rail-based corrosion scanning. This is a service we contract out every 3 years. It assesses our wood ties, the condition on a 4-point rating scale. We also use it to assess rail-based corrosion, which is an issue in our moist tunnels. Additional expected functions are counting of open joints, as well as identification of missing fastening on the track. And this data also is entered into our linear asset management system. In particular, this particular data type helped WMATA a lot understand the true advantages of automatic collected data, as this is one of the first data to directly impact the capital planning program. WMATA is entering into a new wave of automatic track inspections through our ATI initiative, Automatic Track Inspection Initiative. We're looking to blend the technological advancements within track inspections with revenue service hour opportunities using a dedicated non-revenue train set. This is influenced by existing programs at New York City Transit, MARTA, which is in Atlanta, and TTC in Toronto, Canada. The goal is to gain greater precision in track inspections while reducing train delays and safety risk from having personnel on the roadway. And when I say greater precision in track inspections, I mean not identifying duplicative defects or calling one defect multiple different names or explaining it differently where it could be confused as additional defects than what actually does exist. Having this level of precision supports our reliability centered maintenance goal. And we expect to have a release of the RFP for the ATI program coming out this year. Moving on to some of the core features of the ATI, looking at location accuracy and precision, geometry, rail profile, a vision system in which machine learning and an AI role will better identify defects that are currently identified through manual efforts. The items on the right are about a half dozen various items that the vision system will actually find and pick up. ATI will also look at ballast profile, conductor rail or third rail geometry. We'll have infrared cameras and about a half dozen additional optional technologies that we will decide on once a vendor is awarded this contract. The vision data will be reviewed manually to vet actionable items, but as AI developments occur, this will reduce the manual confirmations and make the process a little bit smoother. I now would like to introduce my colleague, Spencer Jakowski, who will talk about data management practices at WMATA. Spencer?
Thank you, Robbie. So I'll be discussing how we collect and utilize this data and what we do to perform our data management. Utilizing all those data sources and as in preparation for our forthcoming ATI vehicle, this poses several challenges. Currently, data comes in all types of formats: hard copies, by means of our enterprise asset management system, Maximo, emails, personal notes, word of mouth, and all of this is on top of the automated data previously mentioned. This requires a methodic process to make sure all data is being used and being used properly. In this, it is easy to miss key information as well as it is easy to gloss over missing data or even mistakes in the data provided. Currently, we perform an annual review utilizing all the information mentioned, and our desks can quickly become overwhelmed with paper as well as the data on our computer. We are reliant on using the previous year's worth of data to forecast what work should be planned for the upcoming year. It is an effort to use as much data as possible, but this can have limited success when performing this manually. Another important data source that is needed to take into consideration is all the previous work completed by maintenance efforts over the previous years, as well as anything that was not on the original replacement schedule. We need to be cognizant to not waste resources to inspect the locations that have been previously worked on, or more importantly, to not duplicate work requests. You can go on the next slide, Robbie. To do all this, to solve this problem, a linear asset management system was determined to be the best option to consolidate all the data sources, to be viewable chronologically and spatially, to quickly observe correlations and trends from the data. Other programs are available that perform similar functions, but WMATA selected Optrem several years back, and this program is now currently known as AssetWise, and it is created by Bentley. Using this program, we are able to create a collection and pool of all the data sources. We require that all new and current incoming data be formatted to be able to be inputted into this program. Currently, all that is required is a basic Excel spreadsheet requiring, at minimum, the date and chain marker to plot within the program. This is not limited to what other information we can choose to include and can provide very helpful information. This has allowed several data sources to be viewed and manipulated all on one screen. This additionally has provided the ability to quickly determine the condition of track assets based off of decided criteria for component review and replacement upon joint efforts between our engineering and maintenance teams. Instead of manually compiling several data sources for one segment and then repeating this process for every other segment of track, one list is created instantly and is ultimately projected to inform our state of good repair. Next slide. This program has allowed us the opportunity to create a unique index for WMATA dubbed our Track Quality Index. This supplies as many data sources as possible to highlight locations for renewal or review, as can be seen on the screen. Currently, we have it broken down into 4 main track components: rail, ties, direct fixation fasteners, and grout pads in which the direct fixation fasteners sit on. Both the fasteners and grout pads account for 60% of our track, with the other 40% being our ballasted track. Using all of our unique data sources for each component and criteria, locations are highlighted for recommended capital renewals. Further consolidating all those data sources onto one screen, we can quickly see where one or more components require extensive replacement, which is represented with the number 2 under the Track Quality Index swim lane, which requires rail and fastener renewal needs. We are currently underway in creating a version 2 to take advantage of more data sources and better define renewal locations. Our intended goal is to incorporate other components and maintenance programs, including our third or conductor rail, champion and servicing programs, as well as replacement of turnouts and crossovers. Additionally, this has provided the potential to create and use as a tool to highlight maintenance needs and priorities, not just our capital needs. This can better align with a reliability-centered maintenance practice to get the most out of an asset. By using defect progressions via our track inspection records or geometry data, and hopefully more frequently with our ATI vehicle, this allows us to better use available track time to prolong assets without requiring extensive renewal during revenue hours. Next slide. Using track inspection reported defects, we can quickly see historical defects as shown here over the past couple years. This includes images to better determine degradation rates and if other factors may have contributed to the defect. Additionally, we are able to see changes in track geometry run over run, currently at a 4-month interval, soon to be 2 weeks upon our ATI rollout, similar to what Amtrak performs on their Northeast corridor. Currently, we are basically creating a digital representation of our track. This provides relatively current representations of the overall quality and condition of the track. Inspector documented defects are representative of real-time conditions. And we are currently working that our automated exceptions are currently being worked into the workflow to provide a better up-to-date representation to decrease that 4-month window. This is all in preparation to implement our ATI vehicle data to seamlessly integrate into the workflow process to better predict and remediate conditions and represent current quality. With several data sources in one location, this also assists with performing root cause analysis of failures and defects. Due to our ability to look back at historical track geometry or previously reported conditions, we can also determine when last work was done by our link with our asset management system, allowing us to assist with work practices and improvements if needed. Last year, we had a sizable chip that came out of the rail, and upon review in OpTram, we saw historical reported defects in the progression over time. As you can see on the screen, the first item that was reported was a negative hand test that was flagged during our ultrasonic run in October of 2018. This is where our UT vehicle flagged a defect, but upon closer and hand inspection, no internal defects were found at the time. As you can see, this was able to highlight a squat, which is visible on the rail surface, despite no internal defects from the UT on the previous slide. On the current slide, an inspector a little over a year later in August of 2019 reported head checking where flakes and spalls are evident on the rail surface. And lastly, on the next slide, as mentioned, only a short 4 months after the flaking and spalling in December of 2019, you can see this sizable chunk of the rail that came out. So 14 months from our negative hand test, there was a rail surface breakout. Thankfully, this was removed prior to any further deterioration or, in the worst possible condition, a broken rail. Using all of this data, we are now able to better classify remediations from our operating conditions to get the most out of an asset. Last slide. Our end goal is to create a seamless workflow from our ATI vehicle to the automation of track work maintenance planning. Beginning with our automated inspections being performed on set intervals, ideally optimizing the intervals, the time between runs to get sufficient, as well as to guarantee quality of data needed. This data will then be loaded into OpTram as soon as feasibly possible, and OpTram will then be able to automatically provide required work, as well as predict when work may be required to prevent threshold exceedances. Work can then be planned and performed, and the cycle can repeat itself. Along with that, in that flow, once data is added into OpTram, engineering can review and analyze the information to better optimize data usage and recommendations to get the most of an asset. Additionally, by the use of the Track Quality Index, our planning department can get an understanding of general track condition and forecast future year budget for capital needs. We currently implemented several of these just over the past year, and within the upcoming year, these are expected to be fully connected. All of this in preparation and soon implementation of our soon-to-be ATI program. Thank you for your time.
Thank you, everyone.
Thank you, Robbie and Spencer. Great presentation about the direction automated inspection and measuring and managing track conditions are going in the transit world. Next, I'm going to turn it over to Sam Doherty from AECOM for a presentation about LiDAR inspection. Sam?
Thank you very much, Todd. Hopefully everyone can hear me. Ryan Bellier is with me, and he's going to share his screen in just a few seconds. So my name is Sam Doherty. I'm a vice president at AECOM, professional land surveyor by trade, and in the business for 26 years. Been in the LiDAR business for about 15, one of the early adopters. My job came with Bottle Aspen during the early days of LiDAR, and we've been involved with it and seen it move forward all the way up to really everything that everybody was talking about on all the presentations earlier and how fantastic it was. And with me is Ryan Bellier. Ryan is an associate vice president. He's a manager of information management solutions with AECOM. He's GIS professional. He's been in the game for a good 25 years. One of the things that we want to talk to you guys today is kind of the advancements of asset data collection through LiDAR, photogrammetry, tablet-based data collection, survey type perspectives, all into one sole source, one solution that really ultimately starts from a feasibility and planning through design, through construction, into operations and maintenance. The ability to capture rapid amounts of data in a small period of time, and then the ability to really put a tremendous amount of intelligence behind that data is something that we really see as the future of the industry as we continue to go through. So with that being said, I'm going to hand it over to Ryan and let him kick us off.
Hey, thank you very much. I apologize. Earlier, I was having an enormous amount of technical difficulties, and I'm on a backup machine. So if you are not seeing or hearing something, please let me know. As Sam said, we do a tremendous amount of work with laser scanning, and a portion of what we do at AECOM is to capture information from the field so that it can be inserted into an asset management system. And within the asset management system that I've used in my time, the most critical element is your asset registry. Do you have a comprehensive and true asset registry? So does that mean you have all your assets? Does it mean that you have the conditions all entered into the database? And quite frequently, the answer is no, and sometimes it's not even close, right? So the position we get put into frequently is to try to go out and capture assets, get their conditions, understand a bit more about what we've got in our rights of way or in our facilities, and try to bring that into a system so that we can use those great IT systems to manage our assets and get more longevity out of our assets, and understand where we might need to do our capital planning. So just a brief overview of the types of scanners that we're using, and some of this has been discussed already in this session, but we do a tremendous amount of work with these tripod mounted scanners, and it's important to know the difference between the types of scanners when you go out to go out and do any sort of automated capture, because the way that you deal with the data that's produced from these different devices is different. You'll have handhelds and specialty systems and truck mounted and tripod mounted, and they all have different types of points of origin where the data was captured, and different ways of looking at the device, at the features that you're seeing out in the real world. So with these tripod mounted scanners, we get a great amount of detail. You'll see millions of points, LiDAR points being captured per second, and they tend to go out through large areas. The downfall of these things are they're not very nimble. If you can't see it, you're not capturing it. So you have to go out and take an approach that's going to look at your area of interest from all different angles. And it's not an impediment. It's a workhorse. It's a big part of what we go out and capture, because we can use something like an RTC 360 and move it from place to place, get a high level of detail, capture a lot of information, location data about assets, in the field. And so, just an example of usage that we've had is, what we like to see out of these tripod-mounted systems is great detail, a lot of information that can get captured. And so, I'll circle back a little bit to what we do with that sort of data after I go through these. So another type of capture device that we're using are handheld scanners, and Sam right here is showing the Leica BLK to go, and this is a somewhat new feature, and these we use for facilities quite a bit. Any sort of tight environment where we don't have to have a lot of room, if you will, for the lasers to expand out. And one of the key element to this thing is it uses SLAM algorithms, and it sort of maps as you go. And so an interesting part of what we're doing with these is we're trying to understand how we can use this type of SLAM technology and this sort of mobility to perform rapid capture. Often we're posed with the question of how can we do this as efficiently and quickly and as cost effectively as possible? And in many cases, the answer lies within these SLAM type of capture devices. And so with those type of devices, this is actually a GeoSLAM point cloud, but it's the same idea. We can capture a lot of walls and facilities. So, in the transportation world, there's an awful lot of linear assets like roads and railways and those sort of things, but there's also facilities that we go through and do condition assessments and those sort of things too. And then so there's some specialized scanning type of devices. We've got the Amber system right there and the backpack mounted systems, and those we'll run a truck system every once in a while, and those are designed to hit special areas, right, where there's a little bit of a hybrid need between all of these things. And so with some of these devices, we can get a very detailed point cloud, and this is the point cloud of one of the bridge projects that we worked on. So real quickly, a great part of these tripods mounted scanners is that we can tag assets while we're out in the field, and that's a really cool element of what we do, because what it allows us to do is have a device that's sort of attached, if you will, through Wi-Fi to the scanner. And as it's scanning, we're able to go and put some eyes on the components that we're seeing. So now we've got a tag on these assets. And we'll see that in the point cloud. So when we go through to develop data like a GIS data set or, Navisworks or Revit, we understand what exactly there is there. And because we have the point cloud, we understand the geometry and location of it all. And then we can put 2 and 2 together. And so my contemporaries say we get the chocolate and the peanut butter and we put it together. And then we've got a nice attributed data set. And sort of, hand in hand with that, we're able to understand what the physical characteristics are about what we're looking at. So when we tag it, we can also, associate a certain, type of condition assessment. Is there a crack in it? Can we read the nameplate and those sort of things? And we can capture all of that. And then as we bring it back into the office, it helps us to more quickly and efficiently build that asset registry. And there you see it in use in one of our facilities that we're in. We're looking at a whole bunch of MEP where we're able to capture, the information in real time. So it was real slick. As we were constructing this facility, we were able to capture the the asset information. So I'm going to go through a couple of screenshots just so you can get a feel of how this data will look when you get sort of the finished product. You might have a linear asset like a pipe that we are using automated software that isolates that geometry, and then that will go right along the pipe and say, hey, this is a pipe, we know that's a pipe, and be able to sort of traverse through the pipe network and put those all on a particular asset class. So pretty slick type of usage. And with these devices, this is an example of how detailed we can go. We were actually seeing real good detail with fire extinguishers all the way down to your fire alarm systems and even cords and faceplates. So real good stuff. We're able to discern a lot of information from the scan. Now, as you're seeing, as we kind of go about these projects, we don't just go out there and just stick a device out there for sort of willy-nilly. We'll walk up to a site and drive around or walk around the site to find any sort of issues where we might have anything that might be an impediment to our scanning process. And, we plan for overlap. We want to make sure that where our scans go through, we get enough coverage so that we've got a dense point cloud at our targets. And then we also look out for traffic and, other transit objects, bikes, dogs, things like that might, pop up in the scan that we don't want there. So we've been talking about rail a lot, and rail is on Sam in my mind a lot here lately because we're being requested to do more and more inventories and rights of ways, and we're being asked to do a bit more survey inside of these areas. And so when you go with if you have a truck mounted type of like a Pegasus system LiDAR device, and you can put it on the rails and go down the rails, you're able to capture whatever is in the right of way and as far as that laser can see. And so, we go through, we'll see something like a switch or a sign or a light, and we'll be able to capture that, in its location. As we go through these, the whole idea of what we're trying to do with our R&D at this point is to be able to look at that 3D geometry and try to automate what type of feature that is based off of its geometry. That's really quite challenging because where there's been a lot of progress with machine learning and AI, the 3D geometry adds an extra element to identification that we don't see with a static image. But so again, some of the challenges, speed. Certainly, if you go really, really fast down a linear asset with a scanner, you're not going to get the same result as if you have a static device that sits there for a couple minutes and takes spot after spot. So you have to plan for those sort of things. Other challenges are certainly safety. If you're in there scanning in a tunnel, you want to make sure that what you have proper lighting and those sort of things, so that you can make sure that you're not putting yourself in any sort of danger. And then the other challenge is linear capture, right? You go in one direction, you go 5 or 6 miles, and then you got to walk back to your truck or whatnot. And so you need to make sure you're planning for the linear nature of it all, because you don't necessarily stop or restart. You want to gain those efficiencies by trying to come back in a circle, if you will. So again, the ground truth is an important part of tying all of this stuff together. We've got boots on the ground, we've got our GIS guys, we've got our automated feature extraction and those sort of great tools, but we have to make sure that we have a lot of ground control and ground truthing involved with these data sets, because it's not just knowing what's there, but where it is. And as you can see here, we'll go out and set control. We'll go out and maybe run some traditional survey, look at it against our results, make sure it's what we expect. And that's what Sam's level of expertise, being a professional land surveyor, is that he's able to get that control, tie it into where the point cloud is. And then now we know exactly where we're finding assets and to what level of accuracy their location is given to us. And so with this rail capture, I kind of talked into this a little bit, but the laser scanning, it really is an efficient way of capturing information in the right of way. And there's lots of environments that make it challenging. This one here is it may not be a significant challenge for the surveyor to capture, but this is a challenging environment for the computers to process it, because we've got a tunnel here where the walls are very, very much the same all the way down. And we've got repetitive assets in the scan, and it's also dark. So there's not a whole lot of color differentiation. So our methods of extracting features using photography or images is compromised by the lack of light, and then our ability to extract images automatically by geometry is compromised by the repetitive nature of the lights and the sort of monotone, boring walls, flat walls that we're seeing there. Sort of just kind of to wrap up this short little presentation on this, an important thing to also think about is, I knew I was going to get this on the backup slide here. An important thing to think about is that when we are going into when we're doing construction, or we're starting in on a construction project, that is an ideal time to get out there with a data capture device, because there may be a lot of items that could be obfuscated by the construction that we would want to capture its location and get that before we go. And it also sort of introduces this asset management at the very beginning of the project lifecycle. So I'll kind of wrap up there. I think we're getting within a few minutes of our allotted time. So I wanted to open up to questions, or throw it back to Sam and see if he's got any closing remarks. But I really appreciate everybody listening.
No, Ryan, I think you covered it really well. I really appreciate your help on this. And I hope that we were able to convey to you that there are a lot of different ways that you can go through the asset management process, and adding, and Ryan didn't even have the opportunity to really get into the UAS photogrammetry, the LiDAR, the combination of multiple iterations, the tablet-based data collection, to really bring it all together into one database is incredibly important. But I think that we are just about out of time. So with that being said, I'm going to throw it back to Barry, and I thank you, everybody, and please stay safe.
Thank you, Sam. I appreciate, on behalf of all of us, the information all the speakers presented. Hopefully for the listeners today, you got a chance to hear what the rail industry is doing. And then, of course, at the end, what the survey industry is doing to support both the rail industry and other means of using LiDAR and scanning technology to support asset management. I guess I've been monitoring the chat session, the Q&A, and I haven't seen anything specific come up on questions. But we have just a couple minutes before we go to the main stage for closing. And I'm going to ask this for Ravi and Spencer, because I think Brad hit this in CSX. One of the things that always hits me on asset management is that there's a lot of data, and we've heard a lot about this, of the data that you capture. And I think Spencer showed a cluttered desk of all the data and the way it comes in. And I think Brad touched on this too, is that ultimately as asset owners, we never have enough dollars to invest in the system to take care of it. So it's a prioritization. And my question would be, and if we have time, Brad, you can pump back in, but I do think you hit this in your presentation. How do you use this in terms of the data analytics and asset management work to prioritize your capital investments when you're looking at your capital program on a multi-year basis? And secondly, do you do alternative investment scenarios where you take a look at, if we put these dollars into this particular need as a higher priority, what would the other assets look like as they continue to decline without investment? So it's a sort of two-pronged question. How do you use the data for capital planning? And secondly, do you do alternative scenarios?
Yeah, that's a great question, Barry. So your first question, we have a maintenance and safety standard, and we basically categorize the defects that we have based off of those standards to determine how severe they are. We also do individual assessments out there, both on the engineering side, teamed up with the maintenance OA side, and we look at the entire environment, not just the track, but the supporting structure, any other external factors such as runoff, water from other places, anything that can affect the integrity of the track, as well as performance of train operations, including of ridership. A higher priority line with more frequent trains would warrant more action than a lesser used line. So we assimilate all that information, and we determine our prioritizations that way. We also look at locations where we have trends of frequent failures. We might fix this one issue, but we have history that 6 months ago, we had another issue there. A year before that, another issue. And then we might do an overall renewal of the infrastructure based on those trends of issues. And I'm sorry, your second part of the question, you're talking about alternate delivery or alternative funding methods.
I can't. Alternative investment scenarios, like do you model, like, okay, if we make these series of investment, what happens to the other? It's, there's never enough dollars. So do you look at different scenarios based on the asset management?
Sure. We do that. It's a team outside of my own. I'm just on track engineering, but we have a team that looks at the finances of WMATA and makes those decisions. They come to us for information. Spencer's been key with that with the track quality index. and assessing different portions of the system, different assets, and determining which ones are in greatest need for overall. But one thing as engineers, we look at redesigns. We look at what do we currently have today, how's it functioning, and how can we design it better? Or how can we change the specifications so it performs better for the future? And one thing we're currently working on that Spencer's leading as well is looking at our electrical insulators for our contact rail. Are there alternate materials that actually have greater longevity and performance? This way we save money by switching to a new material than keeping with our current material and dealing with the existing failure rates.
Great. I appreciate that response. I think for all asset owners out there, I know we're out of time, so I'll wrap it up with this, but I think for all of us asset owners, there's a parallel there to what Ravi just said about the volume of the road. On the highway side, we might look at the higher volume highways and say that might be a higher priority than the lower volume, but some similarities, but a lot of progress being made in asset management and automated data collection. I hope today's speakers gave you an overview and good understanding of where they're at with their approaches and the technology they're using to support it. Hopefully you found that interesting. You have all the speakers' contact information, and based on the time, we need to conclude and go to the main stage for concluding comments. But again, thank you to the speakers, and feel free to contact them with any follow-up questions you may have. Thank you all.
Thank you.
I hope you enjoyed this, and I hope you enjoyed the entire conference. Take care.
Take care.